Hello, everyone. So thank you very much for everybody joining us today. So my name is David Delhamet. I am the Senior Corporate Partnerships Manager at Wiser. So today's topic is beyond classical AI, quantum machine learning for anomaly detection across industries. It is based on a use case that we've done with Fraunhofer ITWM. And when you think of anomaly detection, very often you think about manufacturing, but this goes beyond exactly just manufacturing. It goes with the energy sector, logistics, finance, and many, many others. So this is why we look forward to presenting you what was done during our use case, but also how it can be used in other sectors as well. So just a little bit about Wiser. So Wiser is a science education and research organization that's accelerating the transition of frontier science into real-world capabilities by working with different sectors, different partners, from government organizations to labs to the private sector and scale-ups. So we work with people from different sizes, different organizations. We've trained up to 73,000 plus, and we will have more people to add to those numbers as we've kicked off our summer program this Monday. Also, we're in 120 plus countries, so we really are a global organization. We've done 20 industry projects up until now with 9 different partners, and we have 53 active quantum research fellows and 85 plus quantum providers and strategic partners that we've built over the years. Now, the verticals that we're part of are quantum ecosystems across the United States. One of them is Mountain West, while the other one is in India through the Amaravati Quantum Valley, then in Andhra Pradesh. Then the second thing is self-paced learning. So we have Basic 101 and executive programs for executive learning who are looking to learn more about quantum technology and how they should get started. Then our research arm is exactly what I mentioned, our custom R&D expert teams that are assigned and the IP that's retained by our partners. We have our summer program, as I mentioned, was kicked off, and we will have in the second half of the summer our challenges and an insider program as well to give access to emerging quantum AI tools coming from many startups who are emerging in the field. So first, I will introduce you Dr. Pascal Hoffman, Research Coordinator for Quantum Computing at Fraunhofer ITWM. He is a Research Coordinator in Quantum Computing at the Institute of the Mathematics in Germany, where he develops and applies quantum and hybrid algorithms to various application areas, specifically optimization problems in finance and energy. While Vardaan is a part of the Wiser team, he's our quantum solutions head, and he has a quantum computing researcher with a background in atomic physics and experiment material sciences. And he's in charge of many projects that we've done within the energy sector, logistics, finance, material science, and many others. So I will now pass it on to Pascal.
Yes, I think you can see my screen, right? Information. Perfect. Yeah. Thank you, David, for the nice introduction. So I don't need to say much about the Fraunhofer Institute, but indeed I like to do that. Well, the Fraunhofer Institute is located in Kaiserslautern, Germany, and Fraunhofer is not just one institute, but indeed it consists of many different institutes that are spread not all over Germany, but also we have offices worldwide. And the Fraunhofer Institute for Industrial Mathematics is one of the largest mathematical research institutes in the world. We have over 500 employees from both Germany, but also international colleagues with a lot of publications and dissertations throughout the year. We are pretty much involved not just in research, because we are an applied research institute. We are not just doing groundbreaking research, but we are also doing the application thereof and also trying to advance the industry here. So we have a lot of industry clients that we work together. And as you know, mathematics is everywhere. So our clients are everywhere. And basically we focus on 3 pillars in our research and also application. That is data analysis and modeling. We're doing machine learning, optimization, and simulation methods, and we apply everything together with scientific computing, high performance computing, and visualization to provide the necessary tools for the decision makers. So And with that being said, we are also not just doing mathematics, but we are also doing quantum. And here our role is quite similar as the application-focused research institute that we are suggests. That means we both want to advance the quantum science. That means by actually doing research, but also by preparing the industry and also the transition from theory to practice in the quantum world. And with one sentence, this just says we want to make you quantum ready, but also we want to make quantum ready for you. And what does that mean? First of all, we provide a quite nice portfolio of education measurements. That is, of course, we were also involved in WISER's program, where we, in the past years and also this year, we are providing lectures and also support. But we also have our own research or lectures. We have a basic course. We have also a course for decision makers that don't need to go too deep in the technical details, but just enough so they can understand the capabilities of quantum computing. And besides, we have also subtopic focused lectures like quantum machine learning or quantum image processing that are all certified, so you get a certificate at the end. Research-wise, we have three main pillars. First of all, we have our software stack and compiler, where we're focusing on gate-based quantum computers, on how to build a software stack that starts from the application until the execution of the real device. And for that, we are focusing specifically on the encoding of a problem, but also on how to distribute the heavy lifting on both classical and quantum devices, meaning we have an HPC-QC distribution focus. And we are also doing hardware-efficient circuit learning, that is so-called quantum architecture search, where we are thinking of new ways of finding efficient and this means hardware-efficient circuits that we can execute to solve our problems. Algorithmic-wise, we are focused on all three main pillars that are similar to what we are doing on the classical side. We are doing quantum optimization, where we focus on application-oriented problems that feature, for example, multiple objective uncertain data. We are doing simulation, for example, with quantum Fourier transform, and we are also doing quantum machine learning. For example, we have hybrid approaches that do both the machine learning on quantum side, but also on the classical side, and as well as neural networks, where we will see later something about it. And third, of course, we are application oriented, and thus application is one of our main topics. And this is widespread and attached to the domain knowledge we are having at the Institute. That is, for example, in portfolio optimization in finance. We are doing a lot of image processing, for example, the anomaly detection of building of concrete, that we try to identify whether they can indeed be used to build a large building. We are doing also quantum chemistry. We're doing material simulation to find out whether materials have the expected properties. And at the end, we are doing also real-world application optimization tasks, such as in the supply chain domain. Yeah, that's quite a lot. But for now, we will just focusing on one use case of the main we're having, that is anomaly detection. And the question is, of course, first of all, what is anomaly detection and why is it a real-world use case? Well, anomalies happen in many areas. For example, if you produce goods, you want to ensure that your goods have the right quality. And so you have to ensure that this is indeed the case by measuring, by looking at it, by having the right sensors in your production line to find maybe anomalies, for example, maybe an open, not really closed can if you produce cans. Or if you produce cars, then of course the car should not break down once it leaves the plant. The same is true of if you stay with car, then it also is true that you want to have good quality control once it has been delivered. That is, you're looking in after sales domain to find out when is a maintenance schedule properly done for your car. When is there some anomalies in the car data that you need to address in the next maintenance? You'd also want to do monitoring and security, for example, finding out anomalies in image recognition, for example, to see if some intruders are there. You have in general fraud detection in finance, for example, if you have credit card transactions that just don't add up, or you have in general like also data breaches if you have confidential data. And all of these are anomalies that you try to tackle in the real world, and thus good machine learning models are necessary for this. But with the overwhelming data you're having, complex scenarios that all of these inherently are, and also that you want to have high quality decision or decision support at least, this requires more accurate, versatile, and robust models to find those anomalies, to have both few false positives and literally no false negatives. And that's why we need more and more complex and more better models. And maybe quantum machine learning could be here of help. And this brings me now to an end of my part and handing over to Vardaan, who will address this direct question in his part of the talk. Thank you.
Great. So Vardaan, thank you, Pascal, and now passing it on to Vardaan.
Okay, great. Yeah. Thanks a lot, David. Thank you, Pascal, for the amazing introduction and the setting up the stage for me to take it from here. So yeah, thank you everyone for joining in today. My name is Vardaan. I currently lead the quantum solutions team over here at Advisor. So we do a lot of amazing research, and today our focus would be on benchmarking encoding families in quantum neural networks and the fixed circuit area for frequency, spectrum, and trainability. Okay, that was a mouthful, right? And that is what our paper is also titled, if you want to look it up. But rest assured, please rest assured that today, I promise I won't go into a lot of technical jargon. I'll try to, explain our study, explain our research from a more industrial perspective. And that would be super important, especially if you're coming in from that kind of background, right? So if you want to see where anomaly detection can be solved or these kind of problems can be simulated using quantum, and you want to do production grade research, that is what the perspective of today's research would be. Having said that, and also before I start, I do want to shout out to Martina, Patrick, and Hein, who were the key quantum researchers involved in this research. They were the champions who authored the paper as well. So if any one of you is coming from a more academic background, or you would like to, deep dive and learn more about the technical details, you are more than welcome to please scan the QR code over here and access the paper. It's available on arXiv. We are soon going to publish it to a scientific journal as well. So this is also a very good opportunity for all of you to share feedback to us, right? If you have any questions, if there's anything that you feel we missed out in the current abstract and the current manuscript, please let us know so that we can improve and we can take it to the final submission round. Okay, next slide, please. So we are at WISER, right? So what is WISER? WISER stands for the Washington Institute for STEM Entrepreneurship and Research. We are a nonprofit organization based all around the world, but actually headquartered in Washington, D.C. in the US. But otherwise, we are global. We have impact more than 120 countries till date. But the most impressive thing about all of this is the real world impact that our teams have been able to make. For the past few years, there have been 3 startup spin-offs in quantum computing, quantum communication, and quantum sensing, respectively. We have had more than 53 quantum research fellows actively working with our team, which is in itself one of the considerably larger pure quantum teams in the world. This very much compares and kind of competes with leading quantum companies today. We have had more than 20 successful industry pilots and across more than 85 plus partners, right? So these partners are some of the best of the best of the best in the world. We are very proud to work with all of them. And if we go to the next slide, we can also include some snapshots of some of the partners over here, right? So you can see E.ON over there, which is Europe's leading energy utility providers. We have Vanguard, which is the world's second largest financial institute. And we have legacy institutes like our very amazing Pascal and his team from Fraunhofer. So we like to work with all of them, including startups as well. So you might see a few quantum startups and many, many more, right? So 85 plus partners. I included a few snapshots over here. But the important thing I wanted to highlight in today's talk is that when we are doing these high risk, high reward research at WISER, right? And we want to focus a lot on implementation. We want to focus a lot on industry impact. We kind of create 3 broad pillars where we want to focus our research on. First is we want to ensure that all of our research is somehow applied research, right? We are happy to do fundamental R&D as well, but at the end of the day, there needs to be a very clear implementation from an industry point of view as well. And that is because we do not want to be a pure paper mill, right? We don't want to focus purely on just publishing papers and a lot of papers, and then no one reads those scientific publications. We want to make sure that any research that we do is implemented on real world experiments that's taken up by the industry, because that is what makes more sense. The second is we want to do utility scale experiments. And what I mean by that is that most of the experiments that we do, most of the activities that we run, most of the research that we do on the quantum computing side, we push our limits to make sure that they are beyond 100 plus qubits, right? So no toy experiments today, no proof of, concept kind of projects. We want to push our limits to make sure that anything that we are doing goes to at least a utility scale, at least a scale where people can start seeing what kind of value they're providing today, what kind of value they might be providing tomorrow, and how do we ensure that scalability approach within the industry. And third is benchmarking. And that is, I think, one of the most crucial aspects of any research, because, and this is something which all of you might be much more aware than me talking about that, is that when you are coming from a professional background, at the end of the day, the only thing that matters is your P&L analysis. Right? Organizations only want to find the most economic routine of work. They do not care about whether we are using classical or whether we are using quantum or AI or some XYZ other fancy compute, right? So today, to make sure that we are able to express value in any kind of quantum computing work we are doing, it is vital that we put a lot of emphasis on making that research open and also benchmarking it against the industry standard. So we at Wiser put a lot of emphasis on that. And with that kind of brief introduction, I'll dive right into anomaly detection with the next slide. And I'll pick it up right from where Pascal left it off, right? So he gave a very beautiful introduction of what are the different use cases of what anomaly detection are. And you might have observed that it's everywhere, right? It's not just limited to one specific industry. It's all across the globe. But just taking a step back, right, and understanding anomaly detection in its most, fundamental form, it's just a very critical process of identifying outliers or maybe identifying patterns in a data that do not conform to established normal behavior, right? So anything that is different, anything that is not routine, that is an anomaly, that is a point that we want to consider. And using that detection is very important. The next slide. And all this makes a lot of sense because in industry setting, this anomaly detection easily translates to the early identification of faults, which can further be used to reduce energy waste. It can help us with maintenance costs. It can help us with operational downtime. It can do a lot of regulatory compliance across industries. So all of this makes sense from industry setting. And next slide. So for instance, all of these processes make sense when we tie it back to applications. Just again, picking up from what Fraunhofer slides were mentioning earlier, we have a lot of use cases, right? So it can help us, and Fraunhofer correctly mentioned that it's there in finance, it's there in cybersecurity, in manufacturing. So for example, for monitoring the leak detection, for monitoring cracks and different kind of defaults in manufacturing, from monitoring the electric grid, from monitoring how the networks are being run, if there's any kind of cyber attack or any kind of intrusion detector there. So all of these items would come under the broad umbrella of anomaly detection over here. And it is very important that these real world signals are often implemented by the choices that we make. So next slide. So the question is, okay, well, I do understand what anomaly detection is. It's very important. Understood. It's very important for the industry. It's used in a lot of use cases. All of that makes sense. But why quantum? And why today, right? Why are we suddenly talking about implementing these kind of resources using quantum computing? Well, because humans are greedy. Like in a good way, right? In a good way. Or maybe we are just crazy ambitious and we are not lazy, and that is what makes us human. But the thing is that, right, like in today's ever expanding digital world and the data sets that we are dealing with, they are increasingly becoming more and more complex, right? I mean, even too large for classical machine learning models. So either some classical models are just intractable to handle this kind of data, they are not good at what they do, or maybe we have to take certain choices, right? We may have to take certain assumptions. You might have to do some kind of cost cutting in between to running these classical models, which makes the efficiency not so good, right? So maybe they're not good enough for the critical tasks that you want to handle. So if there is, imagine a nuclear facility that you're working with where it's a mission critical important, and having a fault in some of those facilities could, well, practically result in death. We do not want to take those chances, right? So chances of being inaccurate over there should be zero. It should be 100% result. So in those cases, having less than optimum classical models are not a choice. So today, it is just in the best interest of everyone over here to start exploring quantum machine learning approaches. Not because they might have an advantage today, but these are some very relevant methods and some nice approaches that we should start at least thinking about, because by using these parameterized quantum circuits, right, we can encode the data into high dimensional quantum states. and potentially gain new insights into complex data sets that classical does not know how to do. So with that kind of mindset, right, we want to use quantum. The next slide. So yeah, why isn't everyone already jumping into quantum right away? Well, because it is hard. And also there's the concept of no free lunch, right? We cannot go right into it before understanding the complexities behind doing quantum machine learning. It's a tough job, right? So in the spirit of transparency today, right, I wanted to share some key problems that you might run into if you're trying to implement the quantum neural networks or quantum machine learning for the first time, or if you're trying to scale these approaches from an industry perspective. This is something that you might run into, right? So the first one is just a data loading input-output problem, right? So classical data sets are massive, and convert all of this information into quantum states, which is what we call as encoding or quantum embedding strategies, is slow. It's just slow, right? And that can negate any kind of speed advantages that we might see in the overall algorithmic routine. So there's something to keep in mind, right? Another factor is qubit instability and noise, and that is purely from a hardware limit. And combine it with the next point, scalability and hardware limits as well. So the thing is that quantum machines are not perfect today. And that is okay, right? I'm not a hardware person, so I do not expect to fix these machines. But a lot of researchers are doing active research over there. So even if it's not perfect today, I have a pretty solid feeling that this would improve in the next few years to come, right? And it's kind of a temporary issue which will be fixed very soon. But the last 2 points are very important for all of you to understand. The thing is that even if we have the best algorithm, even if we have the best hardware available, true quantum speedups in a machine learning environment can typically work only if we rely on an existence of a functional QRAM, right? So just like a classical RAM, which works on instantaneous data processing, we also need a RAM on the quantum side, a QRAM as we call it, or a quantum RAM. And we need such a thing to access large databases instantaneously. This technology, this entire concept of QRAM is just unfortunately only theoretical at the moment. So QNNs in practice must be paired with slower classical memory storage devices, and that does not prove very well from a practical advantage point of view. And maybe the last one is that, okay, understood, parameterized quantum circuits can map into higher dimensional quantum states, but just doing that, just having a higher or a more quantum capacity does not always guarantee a better learning experience, does not always guarantee a quantum advantage. So it's very important that we understand all these points, and it's very important that all of us kind of take these in the stride while we are doing research. But yeah, that I wanted to give you a quick flavor of that. It's not as easy as it sounds, right? So we acknowledge that anomaly detection is critical for industries, and it is a very, very important problem to solve. And that is one of the big reasons why we partnered with an amazing organization called Fraunhofer ITWM, based in Kaiserslautern in Germany. And with the quantum experience that we bring in at Wiser, and with the extensive mathematical, financial, and optimization strength that Pascal and his team bring in, we performed a very, very comprehensive study on this particular topic. And connecting it with the earlier ethos of our research that I shared, our work broadly comprises of 3 focus areas. So number one, we want to build the best models out there, the best quantum learning models, quantum neural networks, focus on emphasizing learning capability, understanding the analysis between qubits and depth, and all of this with a very focused approach on industry application, right? The second would be just benchmarking for industry standards. We want to make sure that anything that we do is compared against the industry standards. So there's a lot of effort gone into that. In this particular approach, we not only validated our entire model, our entire approach on 1 data set, not 2, but 3 data sets, 1 synthetic and 2 real-world data sets. Similarly, we tried a lot of encoding strategies to bring the best results out of there. And again, not 1, not 2, not 3, and so on, but up to 6 quantum encoding strategies were demonstrated over here, just with the emphasis that we want to benchmark against everything that is possible, right? So that the reader, the end user, the customer over here can get a bird's eye view of what works and also what doesn't work. So they can make a more strategic decision of what they want to start implementing at their workforce, right? And finally, because this, especially for this particular webinar, right, the goal is to make sure that industry professionals get something out of it. So we also included a roadmap for reproducibility. Okay, you love this approach, or at least you like this approach, you want to start building something from it, take it away. We have made everything open source at this stage. All the code is available in GitHub. It's open source. And we also made a very strategic decision outline that you can take to see what works for you. How do you want to implement? How do you want to start working on these kind of quantum models for your industry use cases? So moving forward, next slide, I'll now take a few minutes to just give a little bit of technical insights, right? I won't bore you, I promise. I won't go into a lot of technical jargon, but believe me, this is a little bit important because you need to understand how quantum neural networks or quantum machine learning in general can be used for anomaly detection, right? So where does this all fit in, right? I feel that quantum neural networks fit into this particular landscape as a specific type of parameterized quantum circuit. So these, boxes and circles and these lines that you see are at a very high level are quantum circuit, right? That is it. And in an anomaly detection pipeline, when you're focusing on that particular use case, QNNs can act as a core classifier or maybe a regressor that processes the sensor data, maybe vibration values, maybe images from a manufacturing plant, maybe something else, right? Some kind of data that it pre-processes that and determines if a system state is healthy or it is anomalous. Is it good for factory purposes or is it defective? Some kind of differentiating factor, right? So if you're aware with classical machine learning, you know how classifiers or regressors work, right? So I won't go into that. But my point is that it works in a very similar fashion. And these models are highly suitable for hybrid setups. And that is something which you should take away, right? So I'm not expecting this entire quantum machine learning model or quantum neural network model to run purely on a quantum computer. That's not what I'm trying to do. But rather, these models are highly suitable for hybrid setups, where quantum circuits handle the information processing and the classical systems help us optimize these parameters, right? So if we go on to the next slide, we can talk a little bit more on the mathematical side for the QNNs as well. So these circuits, the parameterized quantum circuits, or QNN as we'll call it moving forward, they are defined as the expectation value of any parameterized quantum circuit, right? And the circuit in itself consists of alternating layers, data encoding layers, and parameter encoding layers. Very similar to what you just saw in the previous slide, right? So you saw these two layers. One was the data encoding layer, and the second was the parameter encoding layer. So we have alternative layers as part of this entire QNN framework. And now a foundational maybe knowledge or insight that you should take away is that QNNs are in a way equivalent to classical finite Fourier series, right? Why does that happen, or what is that? So basically, the model's output can be expressed as the equation that you see on the screen, right? So this fancy mathematical equation that you see, that is what the model's output can be represented as. And one term over here, say omega, represents the frequency spectrum. So this is important because this omega, the spectrum term, is determined purely and solely by the generators that we're using in the data encoding layer. And this relationship is important to understand because it links the expressivity of a quantum circuit directly to its ability to represent specific frequencies in the data, right? So the fundamental thing is that we need to understand how quantum neural networks maps to a Fourier series, maps to anomaly detection, and what are the different parameters that we want to change while building this entire setup to make sure that we can get the most expressivity from our data set, and at the same time, make sure that our models are actually learning, right? It's not just sitting on some fancy layers, it's actually doing its job. And that is a lot of work that we put into it. I won't go into the technical know-how, how the algorithms are actually set up. If someone is interested, that's homework for you. Feel free to go to the paper that we publish and have a good insight into that. But the next thing I would like to talk about is the data encoding process. So this is, again, a very important topic for everyone to understand here, right? Like this is, in fact, the first step that anyone takes. You have a lot of classical data and you want to put it into quantum computers. That translation of classical onto quantum, that mapping process is called data encoding. And typically we use Hamiltonians or generators to do that, right? So when we benchmark different encoding families over here in this particular study, the idea is that we want to understand a fundamental trade-off between expressibility and trainability, right? So while a larger frequency spectrum might theoretically allow the model to approximate a lot of different complex functions, being a larger frequency spectrum in itself can also make the optimization landscape very, very hard to navigate, right? I'll just double click on that in a minute, right? But just to kind of give you a high-level summary of the different encoding techniques that we have. So Hamming encoding is something that we use as constant subgenerators, and it results in a frequency spectrum that grows linearly under the circuit area, right? The binary and the exponential techniques, the second and the third one over here, they use something called as scaled prefactors to achieve a frequency spectrum that grows exponentially with the area, right? And the last three, ternary, turnpike, and golem encodings, these are designed to achieve more of a maximal frequency spectrum, either in the terms of a large gap-free region or the total number of unique frequencies or something along those lines, right? Sorry, again, if you're not familiar with these jargons, please feel free to ignore. But the point is that, next slide, all this research introduces two key variables in this area. And this was a fascinating kind of observation that we made during our research, is that the area, this is a kind of a variable that we define. The area can be defined as the product of qubits and the layers, right? So for example, A is equal to R into L, R is the qubits, L is the layers, and we want to maximize any kind of output coming from that. The initial theoretical understanding is, that there is spectral invariance over here. So all configurations with the same area and the encoding type should share the same frequency spectrum. For instance, if we have area equal to 6, whether we call that 6 as 1 into 6 or 2 into 3 equals 6, either ways it should give us the same result. But when we are doing this practically, that's not the same, right? So if we have a 1 into 6 kind of approach that is visible in the first figure on the left-hand side, it's a very deep and a narrow circuit. We are using less number of qubits, but with very deep circuits. On the other side, on the right-hand side, if you see, we also compare it to shallow and wide circuits. So that is where 1 into 6 is converted to 3 into 2 kind of a scenario. So now we're using 3 different qubits and splitting our workload across 2 kind of blocks over there, right? And this is far more better than 1 into 6 kind of approach. Just as an example, right? So this is something that we do want to promote a lot, encourage a lot into research moving forward, right? That if, despite that spectral invariance kind of thing, where we do theoretically say that if the area is the same, encoding is the same, it should have no problem. Practically, we do see that despite that invariance, trainability does depend on the shape. And in fact, it depends a lot on the shape. Configurations with more qubits and fewer depth generally perform better and converge more stably, right? So this is maybe an insight that you take away, that if you are building these kind of models, if you are working on QNNs, especially if you're looking at scaling these approaches up, it would be better if you focus more on qubits and emphasize that the depth of the circuit is as low as possible, right? So our benchmarking initiative does not complete over here. We also put a lot of emphasis on validating our models across multiple data sets, right? Again, something which was not particularly required, but we put that extra effort only to make sure that it's validated, it's benchmarked across multiple type of data sets, right? So there were 3 data sets that we typically considered over here. The first one was more of a theoretical stress test data set. This was a random Fourier series, right? A synthetic data set, as you might call it. But the second 2 are important because second 2 are real-world data sets, right? No synthetic stuff over here. So the first one was from Fisher Technique Fabric for pneumatic leak detection. And the third one was from NASA about ball bearing fault data, giving us vibrations from the ball bearings, right? Both the kind of data sets are publicly available. They are available and linked, also cited in our paper and on our GitHub repositories as well. In a couple of slides, I'll share the QR code as well. So if someone is interested in working with these data sets, you can always take a snapshot. But now coming to the results, right? I just took one over here for the interest of time, and I'll double click on the results we got from Fisher Technique Fabric about pneumatic leak detection. And I won't go into specific details of what these results mean or something like that, right? But I'll focus on the high level picture over here, is that the results were really good. Touch wood, right? Our team received a lot of good results from all the data sets. But something which is even more impressive to observe is that on the spot, it's on the spectrum optimization side, right? So larger spectrums does not always turn out to be better. In fact, the best results actually occur when the frequency spectrum is tailored to the target function's complexity, but at the same time, it is compact enough to actually prevent the model from struggling from any unnecessary coefficients, right? So we had to find the middle ground over here. Not too big, but at the same time, also compact enough to do some good stuff. And next slide, please. And that is where we started understanding a good strategy on what kind of encoding technique should one use. So number one is that you need to select an encoding strategy where your frequency spectrum matches the complexity of your pre-processed feature. And that is purely on a data set, right? So this is not a case of one approach fits all kind of thing, right? We try to generalize it a lot, but still, depending on what kind of data you are using, there needs to be very specific analysis of what kind of encoding technique you should be using, right? Generalizing binary and exponential are kind of the most robust techniques for most applications, but again, it might differ a lot depending on what data set that you're using. And the second is that do not automatically choose the most complex, the most largest possible spectrum like Golem or ternary or something like that, right? Unless, of course, the task explicitly requires it, but making it the most, biggest possible spectrum, it might make the spectrum too large that it can actually degrade the learning capabilities. So it's important you find the sweet spot in between. It's important that you find that Goldilocks zone, as we call it, to capture the entire function, but at the same time being compact enough to actually give any kind of practical trainability, right? And with this, we kind of conclude on the results. But the most important thing is, what do you do with all this technical jargon? What do you take away? What do you do when you start implementing at your industry, at your workplace? And that is where we implemented a kind of a roadmap. Again, this is not to scale. There might be differences. There might be small technical data points that would be very, very specific on the exact use case that you're targeting, or maybe the exact data sets that you're working with. And that would be very customized. But on a general sense, it starts with formulating your cost function, right? So first step is that find a problem statement and map it to a Hamiltonian. That is it. And then start assessing the data bandwidth as step 2. One small insight that we have is that if the target function is highly complex, then sure, let's continue working with QNN. But in case the target function is not that complex, please do not spend your energy into doing all of this quantum stuff, right? It's nice, it sounds cool, but classical models might give you a much better advantage right away, right? So a low complex function, just do it classically, right? No need to go for quantum just yet. But if we are moving down the quantum side, right? If we are working with QNNs and quantum machine learning models, it is important to also determine the compute budget, because we don't have infinite money. Or maybe even if we have infinite budgets over here, the quantum machines are still limited. We only have like odd 100 qubits or something, right? With a lot of noise and with a lot of constraints and everything. So it's important you define what is the budget for you. Is it something that you want to compromise with the efficiency of the models, or is it something that you want to maximize to get the learning output as most efficient kind of thing, right? So defining that kind of compute budget is very important. And it could be in a different ways. One we suggest over here is having a variable area that is qubit into the depth layers, and then deciding the area shape. That is where step 4 comes into the play. So again, like I mentioned, if we have an area equal to 6, you could have it as 1 into 6, or you could also have it as 3 into 2. Either ways, you'll get some models working, right? But it's in the best interest of everyone that over here, we emphasize more on distributing our area over number of qubits. So more number of qubits are better than having more number of layers, if that makes sense, right? So deciding which area shapes make the most sense is a kind of an iterative approach right now. We do not, unfortunately, have a clear-cut answer to this, but at least with the know-how that we have, we want to start thinking about these things. And so maybe the last one is which kind of implementation strategy you want to use, like Golem or binary or exponential or ternary or something else, right? And that is exactly depending on your data set. Do we want to have a robust optimization kind of thing, right? Choose binary. At least that's what our observation tells us. But if there are instances, if there are very particular data sets where we want to find very, very fine calibration of the expectation values, and we are not that interested in the runtime or kind of resources that we are using, maybe Golem is a better approach, right? So again, if you want to look at the data sets that are over here, if you want to look at the open source GitHub repository, if you want to look at the paper, please feel free to take a screenshot of this slide, scan the QR code, and everything is open source. So we made it a very conscious decision to make sure that everyone has all the resources to get started on this, because today, with the quantum industry, we want to work with everyone. We really want to work with everyone. With more than 85 partners, that's just not for, shouting it from the rooftops that, hey, we work with everyone. No. We really want to make this a collective approach. And when I say we, this is not just Wiser, right? This is equally important for Fraunhofer as well. We are both in that ecosystem where we want to collaborate with as many people as possible and really encourage clients and motivate more and more people to start valuing what kind of advantages we may or may not get from quantum computing. Okay, so that was a lot of it. But yeah, with that, I'd like to wrap up today's session. Thank you, everyone. You have been a great audience. I was seeing a lot of questions pop in the chat as well. So maybe this is a time where both me and Pascal can attend some questions. If you are interested in connecting with me, you can always email me. You can always connect with me on LinkedIn. You can just type my name on LinkedIn. It's the same. And yeah, I'm happy to take it forward, right? Having said that, we also have our very, very amazing David over here hosting this session. So if there are any particular folks coming in from a professional perspective, interested in industry collaborations, I would rather have you reach out to David because he would be the best person to guide you on the next steps over there. Okay, so yeah, thank you, everyone. And yeah.
Great. Shall we take a few questions? Perfect. So one of the questions we have here is, how are we assuming shallow wide circuit better over deep narrow, more gates give us more accumulated noise gate error rates?
Correct, yeah. So we took that decision on a couple of metrics. So one is scalability. We wanted to understand which kind of, like, from these two approaches, which one is more scalable, right? So I'm not talking about A rise equal to 6 anymore. I'm maybe talking about A rise equal to 50, where there are a lot of iterations how you can break that down into multiple type of shapes, right? And at that point, it is important to emphasize of having more qubits rather than having more layers. So both are, to a point, disadvantages, right? You want to have less number of qubits and you want to have less number of layers. But if you want to pick one of them, it's better to choose qubits over the layer. But that being said, it's not generalized. You might want to work on clear data strategies and understand what works for you. It's an iterative process. So you'll have to run and check every approach to find which is better.
Now, there's another interesting question here. Can we use Anomaly in genomics, radiation planning systems, and in radiology?
I mean, in general, you could do that. I mean, there's multiple ideas what you can do there. For example, in genomics, you could mean that anomalies could mean rare mutation patterns, for example, in the DNA or unusual gene expression profiles. So that could be something you want to detect. The same holds true, of course, for radiation planning or radiology in general. You could, for example, if you have like a radiation theory planning for to fight on cancer, you could say, okay, you have like maybe some anomaly detection assistance that checks if your plan heavily deviates from well-known radiation treatment plans, and if so, it gives you like a flag and say, hey, are you sure that, for example, this dose could be maybe inflicts any problems to some vital organs? So are you sure? So that could be also the case. So I think it could be indeed useful for practitioners in medicine to have some AI anomaly detection assistance to fight errors that might happen if you have to make fast decisions.
Great, thanks. Another interesting question. How can we use quantum anomaly in cybersecurity and blockchain, especially that blockchain is talked a lot these days in being implemented in banking infrastructure and everything?
Maybe I can directly follow up on this as well. I mean, with blockchain, you have, of course, transaction, as you also have in the classical finance world. So you can do fraud detection on like fraudulent detections. If, for example, some wallets do transactions that are maybe misleading, that, for example, should not be for example, if there are high shifts of large set of coins, then of course that should be maybe flagged. But also you could think of what in another way, that, for example, if you are on decentralized exchange and you fiddle with, for example, the gas to try to front run, then of course such behavior could also be an anomaly, that someone tries to front run transactions and thus be in a better position, and that could also be maybe penalized by the decentralized exchange.
Great, thank you.
Got it. And maybe if I add a couple more thoughts here. So yeah, thanks for that, Pascal. And maybe one quick example I can share with what we are already doing is with one of our amazing partners called Vanguard. So that's the financial institute, right? And that is a problem that they are super interested in. So what we're working with them is exactly this. We want to identify anomalies in different kind of transactions. And these are real-time transactions, right? Because they want to process if any kind of frauds are taking place. So for example, if at middle of the night, there is some transaction from your credit card. Now, the location is that, okay, you are still in your city, you are sleeping, you're most probably, sleeping at night. But if your credit card is still active at that point, it creates an anomaly. It's not routine pattern. You're not always doing transactions that's 2 a.m. in the night. So those kind of anomalies are very important to get triggered immediately in those data sets so that the banks, these financial institutes can take action. And it's not just that simple, right? You might have heard of money laundering, which is the bad action players always do. So to prevent money laundering, we need to identify patterns, anomaly patterns in huge transactional data sets to understand, okay, this is something which is being repeated, or maybe this kind of workflow is being applied for certain values, or certain sums of money, which is being rerouted through different areas and coming back or something like that, right? So those kind of patterns are just difficult for human eye, and they're even difficult for classical machine learning models because the data sets are just too complex. So to understand that, sure, we could definitely start exploring where QNNs and quantum machine learning models in general can be used over there. So yeah.
Great, thank you. And maybe one last question. Could quantum ML eventually detect anomalies in complex systems such as financial markets, climate systems, or biological networks that classical AI cannot model effectively?
I am a crazy optimist, so I'd say yes. Yeah, sure. We can definitely do that. If the question is, can we get an advantage out of that today compared to the classical state of the art? The answer is probably not immediately. But ask this question again in a couple of years and we'll have a better answer for you. Pascal, any thoughts from your side?
Yeah, maybe I will play the realist of both of us. Of course, I want to emphasize that as of now, we don't have any quantum advantage. I mean, while there have been claims, especially by hardware manufacturers, I mean, as to the best of my knowledge, all of these claims have been made invalid by research on the classical side. So which is, but from my point of view, nothing bad, because I mean, if there's a competition, you always end up with a better solution at the end. Nevertheless, quantum has this initial capabilities and everything. So I would say, while we don't have quantum advantage yet, I think the research, especially in quantum machine learning, is quite at the beginning. And so we haven't seen like the full capabilities, especially as we need better and more efficient hardware. With that, we could maybe have more complex models on for example, more complex neural networks. And with that, I think we will probably, as we have seen also on the classical side, that what current AI is doing is beyond the imagination we had maybe 10 to 20 years ago. The same holds true for quantum. And so I would say it's plausible that, for example, distinct patterns that you maybe face, for example, in the weather, that is like highly chaos theoretic mechanism, that this will not be grabbable by classical AI, but you need like the special ingredients of quantum to fully grasp up, maybe have a good way of, for example, simulating weather or cloud moving behavior, which is something where classical weather models still struggle. So that could be a way for where quantum could help, and which has, of course, then if we spin this a bit wider or further, we have a graspful of application areas where this could make a difference. And this is just one example.
Wonderful. Thank you, Pascal. Yeah, and so we are over time, and we thank you for staying a little longer and for asking your questions. So once again, if you have more questions, do not hesitate to reach out to Pascal, Vardaan, or myself, and we will do our best to answer any more of your questions, or maybe doing projects together, through Fraunhofer, ITWM, or Wiser, or the three of us. So thank you again for everyone, to the speakers, and also to the crowd for joining. And yeah, keep an eye on what we're doing and for our future webinars. Right? See you, everyone.